afternoon. Yeah, my name is Gerhard Kminek, and I was asked to give you a presentation about planetary protection today. And I think I will start the same way that Professor Schwartz started in the morning and tell you first what it isn't. Because the name is a little bit misleading. Planetary protection is not about asteroid defense. This is covered in our Space Situational Awareness program, mainly through the NEO group. It is also not about space debris. Again, partly covered through our SSA program. Then we have a specific office dealing with the implementation of space debris, the Independent Safety Office, which is then also supported by the Space Debris Office at our Operations Center at ISOC in Germany. It's also not about cultural or natural world heritage. You see here a picture of one of the Mir landers and some of the things that the spacecraft ejected during the atmospheric entry and landing sequence. I could have put also a picture here of a Viking lander or an Apollo lander, protecting these sites, these cultural sites of mankind, or protecting some natural environments on planets or moons, like a crater or a volcano, is not covered under the term planetary protection. On Earth, this is covered by conventions and related to the UNESCO activity. For space, there are scientists that are concerned about this, and they have discussed how to protect some of the man-made and natural features on moons and planets in our solar system. They are currently discussing that at the panel on exploration in the Committee on Space Research, it's COSPA. Again, not covered under the mandate of planetary protection. It's also not a green party for Mars or for space in general, and it's not about playing around with guns and ET. So what is it? It's actually, the scope is quite limited and relatively simple. It's to ensure that scientists can do their work properly, and specifically related to science of the origin of life and the distribution of life. It is therefore also protecting our investment in space science. If we go to other planets or moons, we don't want to discover something that we bring along from Earth, because we can do that much cheaper. And it also ensures that some of the unique opportunities that we have going to some of the planets or moons are not compromised. And with a unique opportunity, I mean in particular learning more about prebiotic chemistry and the origin of life, something that is very, very difficult to do on Earth. We can go back to a certain level, but we cannot go back to the to the beginning of life, because of the very active geology we have on this planet, and because of biology itself, which eats up some of this, or was eating up some of these features. Now, this is the forward part of planetary protection, when we control the contamination of planets and moons, while sending spacecrafts there. There's also a backward part that ensures that when we bring back samples from other planets or moons, that they don't pose a hazard for the terrestrial biosphere. This is usually the term backward contamination. It is, of course, simple prudence to protect our planet, our biosphere, in line with the precautionary principle of environmental protection. And we as space agency are just one player in this second element of planetary protection. There are regulatory authorities that oversee that, and we work together with them. Some history of planetary protection. Planetary protection is by no means a new discipline. It started at the time of Sputnik, when the first group of scientists voiced their concern that some of the exploration activities planned at that time, I mean 57, 58, could actually have negative effects or compromising future scientific exploration. The forum for this discussion was at that time the International Astronautical Federation, UNCOPUS, and last but not least, the US National Academy of Science. They have in 1958 requested the help of the Council of Scientific Unions to evaluate the potential of negative effects and to find appropriate mitigation measures. And the ICSU, now they have a new name, but the ICSU at that time established an ad hoc committee, CDEX, that developed a code of conduct for planetary protection. Later on, the responsibility to maintain and update this code of conduct was given to COSPA, to the Committee on Space Research, which for a certain period of time had a consultative group on potential harmful effects of space experiments, which later on became the Panel on Planetary Protection, which still exists today. Now, the first spaceflight missions that have used this code of conduct were the spacecrafts, the Ranger Block 1 spacecrafts, the first three, in 61. And they used the code of conduct very carefully. They sterilized a good part of the spacecraft with ethylene oxide. At that time, the quality control was not as you would, as we have today. So they had a number of problems with material compatibility. And, but at the end, they made it within the Ranger program. And since that time, all planetary missions that leave Earth orbit have to implement planetary protection requirements to various degrees, depending where they go and what they do. These regulations are not cast in stone. If we learn more about the bodies in our solar system or about biology, we update this regulation. This is done in a usually an international forum, most of the time through COSPA scientific assemblies and dedicated workshops and colloquia, to at the end find a consensus within the scientific community to either keep the regulations as they are or change them. Now, I mentioned before that the regulations actually go back to the late 50s. The legal framework for planetary protection, however, was only put in place in the mid-70s, in the mid-60s, 67, with Article 9 of the Outer Space Treaty, which states that the signatories should explore space in a way to avoid harmful contamination of Earth, of course, and the contamination of celestial bodies. What does it mean now for a flight project to implement planetary protection regulations and requirements? I said before, it depends what you do and where you go. There are certain missions and mission target body combinations where you don't have to do much. You just have to, in principle, write a memo. Some other missions you have to do some trajectory analysis. Rosetta was mentioned this morning. The only thing they had to do, because they had a Mars swing-by maneuver, they had to demonstrate that they will not crash on Mars with a certain probability. Then, of course, if you go to Mars, in Mars orbit, or land on the planet, then you have more stringent requirements. And I will go through them to illustrate some of the technical requirements that in principle, all Mars missions had to implement since the very beginning, including the Indian orbiter that just inserted in the Mars orbit. There are certain type of analysis that has to be provided. There are constraints, for example, on the probability of impact of launcher upper stages. And the reason for that is twofold. First, the upper stages are not very clean usually. They're not assembled in clean rooms. And second of all, if you put an upper stage on a planetary body, you don't gain any scientific knowledge. So the constraint for the upper stage is quite stringent, but it can be done very easily by a launch bias away from the planet. Then there are also some constraints on the spacecraft itself. If you're an orbiter and you go in orbit around Mars, there are some stable orbits, and you have to demonstrate that you will stay up there for a certain period of time. If there's some scientific reason to go to a lower orbit, for example, and the Mars Reconnaissance Orbiter that is giving us these great pictures for the last couple of years is in a low orbit that is not stable, then you have to demonstrate when you enter the Mars atmosphere, in principle, the spacecraft will burn up. And that they have done. Some parts of the spacecraft will not burn up. There's a specific allocations for that. And for other parts where the allocation is exceeded, you have to implement some biological controls before launch. To put things together under biological control requires also some specific infrastructure. Infrastructure, I mean mainly clean rooms. Bioburden controlled clean rooms, typically of class 10,000. Quite similar to the clean room environment used in the pharmaceutical industry. We actually worked together with them. First we took most of their requirements on board. Then we tailor them to our needs, and now there's actually the feedback time where we give them back some of our updated requirements and operational methods, and some of that they take on board because we use the clean rooms differently and found some issues that they didn't find when they qualified or when they validated their procedures. So special clean rooms and garments when people wear this full body suit garment, and of course laboratory to verify that the contamination is properly allocated. Now to meet the overall biological contamination constraint for a spacecraft that lands on Mars, you have to sterilize more or less 2/3 of the entire spacecraft hardware. That is actually not that difficult because a lot of the hardware we use in spacecrafts are quite resistant to heat. So we sterilize, for example, the entire structure, parachute, the harness, the cables, multi-layer insulations, and so forth. The rest of the spacecraft is properly cleaned with alcohol or other solvents like acetone or hydrogen peroxide in liquid or gas form. And then you have to track all this biological contamination of several thousand items through a large number of assays during the integration and test before you launch the spacecraft. This is now one of these examples, is the ExoMars 2016 landing platform. That's the flight unit 2 weeks ago that is currently integrated, and this implements all the typical needs for biological control of Mars spacecrafts. Now, if you have something clean, you want to protect it, of course, from recontamination, and there are different critical stages of the spacecraft build and test phases. Here you see one of the big vacuum chambers and the Mars Science Laboratories inside. Test chambers are one of the critical sources for recontamination, so when you pick the test chamber, you have to be aware of that, and you might have to condition the test chamber properly. The other source is during the launch. You have a lot of vibration that can distribute contamination of the launcher fairing. Again, I'm not sure if the laser works. Yeah, this is a picture of the launcher fairing of Atlas V and the Mars Science Laboratory inside. It's a 5-meter diameter fairing, same as the Ariane 5, a Proton. So You have quite a large surface area to clean. Some of the acoustic panels inside, these are acoustic protection systems to ensure that the sound during launch doesn't break your satellite. It dampens this. Are made in a way that you can clean them easily. Some other launchers made them in a way that you cannot clean them easily. So you actually have to sterilize all the panels, which is not difficult, it just takes some time. And then the spacecraft, the capsule itself is also equipped with recontamination prevention system. Usually there are HEPA filters. You need to equilibrate the pressure during launch, and also when you enter the Mars atmosphere. You just don't want to put a hole there. We put a filter in the hole. So you have a big metallic HEPA filter about that size that ensures the recontamination is controlled. And the filter, of course, is useless if you don't close the other perimeter of the spacecraft. So whatever is, all the interfaces are actually sealed, usually with a silicone seal, to ensure that the only exchange of air is through the filter. Last but not least, landing site selection is also an element where some of the regulation play a role. There are some areas, specifically on Mars, that have environmental conditions that allow terrestrial organisms not only to survive they can almost everywhere on Mars, but to multiply actually. So these areas on Mars, if you want to go there, you have to fulfill more stringent requirements. So this has to be taken into account in the landing site selection. This is now one picture of the current process going on for the ExoMars 2018 landing site selection working group. So this is for Mars. If we go to the outer planets, some of the moons of the outer planets, we have also regulation. These are example now for Europa. The regulation are expressed differently, and you have seen before you can meet the planetary protection requirements for Mars missions mainly with controlling the biological contamination of the flight system. For the outer planets, you mainly control the trajectory and the impact probability. Again, there are different ways how to meet the needs depending on the orbit of your flight system. You can go for a more complicated implementation, or you can go for a more straightforward implementation. Juno and JUICE, NASA mission flying to the Jovian system, and an ESA mission currently under review for the implementation phase, cover both extremes. Now the challenges for the future, and there are mainly two that I will address here. And the first one is sample return from the outer planetary system and from certain moons of the outer planetary system. A couple of years ago, Cassini discovered some water plume on Enceladus. Very interesting, very exciting news. After that, they've also analyzed what actually comes out from these jets on the south pole of the moon. What you have, the situation you have today is not so much the question is Enceladus an habitable environment or the ocean under the ice, but more is it inhabited or not. So people, of course, are interested to fly there and grab a sample from the jet, bring it back to Earth for analysis. We have now similar evidence, less convincing for Europa. And also there are some ideas to fly them there, first through the jet and maybe later bringing back some sample, if this is confirmed on Europa. So what are the needs for planet protection? The needs are to develop more regulation for this sample return mission, because so far we regulate the contamination of the body so that we don't contaminate Europa, Enceladus, Titan. We don't have regulation in place if we bring back samples from this body. Was just not necessary so far. So what we started now last year is within COSPA and the scientific community to discuss what regulation we should put in place so the mission planners that will propose missions like that know exactly what they have to meet. And the next one is human Mars missions, and that's not a mistake that I have the moon here. Because that was actually the first time when planet protection, or at that time planetary quarantine measures have been implemented. They had a very comprehensive program in place overseen by an interagency committee. And they had to go through a long process of validating the procedures, also the transfer between spacecraft elements, retrieval, and quarantine of samples, crew, and spacecraft in an 8,000 square meter facility in Houston before, a HEROES reception was possible. And we have the same problem with Mars, but a little bit more, because for Moon it was not clear, but it was less convincing evidence at the beginning that there might be life on the Moon than we have for Mars. So for Mars we have started a few years ago in the international arena to develop some guidelines for human Mars missions. And now the next steps for the mission planners, important for the mission planners, is to develop detailed technical requirements so that they can actually plan the flight hardware and they can plan the mission operation. Again, we have started that, NASA has kicked off a study on the requirements with international participation, and we are currently going through some of these evaluations. Next meeting actually will be in 2 months. So on the concluding remarks, I will not go through them. I just wanted, I think, to mention two that I think are important. The first one is that planet protection is an enabling capability for some types of missions. And to get this capability, we work a lot with commercial companies to develop the measures to control some of this biological contamination. And the second one is implementing these measures make a more robust spacecraft. Or in the words of the Viking project manager, it was a long time ago, better parts make a better machine. Thank you for your attention.